Okay, so I'd like to start with an example of using the Jacobian. And then after we've done an example, we'll turn to the problem of real interest, which is integrating over space-time. But for now, we have got, we have got dx dy, and this should be equal to the Jacobian times by dr d theta. So I want to repeat this example, but now using the Jacobian. And we know that x will be equal to r times by the cosine of theta, and y is equal to r times by the sine of theta. Now, what is the formula for the Jacobian? Well, the Jacobian is equal to the magnitude of the determinant, and we should have dx dr, dy dr, dx d theta, dy d theta. Okay. So let's see what this is. It's the magnitude of the determinant. Now, dx dr is just cosine of theta. dy dr is just the sine of theta. Now let's go dx d theta. Remember, d by d theta of cos theta is minus sine theta. So we'll just get minus r sine theta. And dy d theta will just be r times by the cosine of theta. Good. So if we calculate that determinant, what do we have? Well, we have cos theta times r cos theta, which is r times by cos squared theta. Then we get minus, and then we have minus r sine theta times sine theta, which is minus r sine squared theta. Well, this is just r cos squared theta plus r sine squared theta. Cos squared theta plus sine squared theta is 1, so we just get the mod of r, but since r is positive, we just get r. So the Jacobian is r, and we learned that dx dy will be equal to r dr d theta. So this is exactly what we argued for previously. I just hope that you now have some understanding of exactly what the Jacobian is calculating for us. Okay? Now, the Jacobian isn't restricted to changing from two variables to two variables. You can write down an analogous formula when you change from n variables to n variables. And we're going to jump right now to the problem of interest, which is that let's imagine we integrate over space-time. So we've got d4x, okay? This we can think of as dx0, dx1, dx2, dx3, or perhaps in slightly more familiar language, this is dt, dx, dy, dz, okay? And let's imagine we move to some other Lorentz frame, and the integration measure in that other Lorentz frame would be d4x primed. So this will be dx primed naught, dx primed 1, dx primed 2, dx primed 3, and again, maybe more familiarly, dt prime times dx prime times dy prime times dz prime. And we would like to know how are these two integration measures related? Well, we know the answer. d4x will be equal to the Jacobian times by d4x prime. Let's just write down what the Jacobian is, okay? We'll just do it in complete gory detail because, well, let's just try to be as explicit as possible. So the Jacobian will be the determinant of dx0, dx primed naught. So I'm taking a derivative of the old coordinates with respect to the new coordinates. And let me just make sure I'm going to be consistent with my convention so far. Yes, dx prime 1, then dx naught, dx primed 2, dx naught, dx primed 3. Then we've got dx1, dx primed naught, dx2, dx primed naught. Oh, let's just extend this a little. dx3, dx primed naught. Good. This is the matrix we're taking the determinant of. Then we'll have dx1. Let's just fill all of these in. Sorry, there's no fast way to do this. You just have to be patient. Write them all in. Okay. dx prime 1, dx prime 2, dx prime 3, and dx3, dx prime 1, dx3, dx prime 2, dx3, dx prime 3. So you'll calculate that determinant, and then you'll take the absolute value of that determinant. Okay? That'll give you the Jacobian, and that'll be the factor that relates these two integration measures. Now, as one of the exercises in the notes, I've asked you to calculate this Jacobian for a specific example. For example, for the boost along x that we were looking at, you could very easily calculate what is this Jacobian. And what you'll find is the Jacobian for any Lorentz transformation is just 1. And that means the integration measure in the original frame, d4x, is actually equal to the integration measure in the primed frame, d4x primed. Okay, now I'd like to give you some intuition for this result. Okay, so what do we have? So d4x we can write as dt, and then d3x. And by d3x, I mean dx, dy, dz. Okay, and we're saying that this is equal to dt prime times by d3x prime. Now, let's think about why the integration measure is invariant under a Lorentz transformation. So one type of a Lorentz transformation is a rotation. So under a rotation, you would not change t. T doesn't change under rotation. So t would be equal to t primed, and dt would be equal to dt primed. So on both sides of the equation, those two factors would be equal. What about the rest? Well, d3x is the volume of a little box of sides dx, dy, dz. And you would rotate that so that the sides of the box now were dx prime, dy prime, dz prime, or d3x prime. But you know that rotations don't change volumes. Think about a box. If you pick up a box and you rotate it, you certainly don't change the volume of that box. And because of that, d3x, this little volume, will be equal to d3x prime, that little volume over there. So it's quite clear why d4x is invariant under rotations. Rotations don't change the times, and they don't change a spatial volume. So dt will be equal to dt prime, and d3x will be equal to d3x prime. Good. Okay. Now, what about Lorentz transformations? Well, Lorentz transformations certainly do change times because we've got time dilation. Okay. So time gets dilated, time gets stretched out. So dt, over here, we have time dilation. So dt gets bigger. By what amount does it get bigger? Well, by 1 over the square root of 1 minus v squared over c squared. That's the time dilation factor. If we think about the volume gets smaller due to length contraction. So only the side that's parallel to the boost will contract, okay? The two sides which are perpendicular to the boost direction don't contract. So remember, x prime was some non-trivial function of t and x, but y prime was equal to y and z prime was equal to z. So only one of these sides will length contract. So the volume will get smaller, okay? And it'll get smaller by an amount 1 minus v squared over c squared. So the volume gets smaller, the time dt gets bigger. The amount that the time dt gets bigger is 1 over the square root. The amount that the volume gets smaller is the square root. So the product of these two factors is just 1. And that means d4x, which is the product of dt with the volume, is invariant. And that's how you should think about the fact that the integration measure d4x is actually a Lorentz invariant. It doesn't change when you Lorentz transform to another frame.